Hello, and welcome to Week 5 at OSH 200, Measures of Safety Performance. Here in Week 5, we're going to discuss some math and statistics fundamentals that you'll need to know and be competent at as you go forward in measuring safety performance. Whether we're analyzing trailing indicator data or we're looking at leading indicator data and trying to find out if their hazard controls are working or if the organization's safety performance is heading the right way, there's some fundamentals you're going to need to know. Now, keep in mind, this is an introduction. We're talking about some of the common statistical functions that are used in safety performance measurement. It is an introduction, it is the beginning. A more in-depth, independent statistics self-study or even taking a course in statistics could prove helpful to you. But at least you've got a foundation and a starting point that we're talking about here in Week 5, some of the essential tools that you would put in your toolbox. We're going to discuss calculations and formulas here in Week 5, but more importantly, we're going to also discuss the application of these, understanding when do you use this, what is the utility of this statistical function or this control chart or calculating something like correlation. Knowing when to use it, what its application is, and what it really tells you is just as important as knowing the formulas. So why are sound math skills for safety performance measurements so important? Well, our metrics, our measurements should always be reliable and accurate. As we've discussed in this class, there's a difference between reliability and accuracy. Reliability meaning the ability of this measure of this metric to be produce similar results over a period of time, whereas accuracy deals with its ability to reach a certain desired standard, such as the target, the bullseye on the target. A firearm's ability to reach the bullseye deals with its accuracy. Now, its reliability, it could be inaccurate, but it would still be reliable. If a firearm shot high and left on a target, not hitting the bullseye, we would say that firearm is reliable, but it's not accurate. It's not meeting that standard, meaning the bullseye. We want our measures to be both reliable, accurate, and as we've discussed, as we go into leading measures, we also want them to be precise. We have to be able to analyze the data that we collect and that we send out to the stakeholders in an organization to use. We have to have the tools to analyze the data. We have to have useful comparisons between the results that we've analyzed and what are our goals. We have to look at trends and changes over time. We have to validate our hazard controls, particularly in that strategic process that was discussed during week 4 before we're investing time in measuring training or we're investing time to measure an observation program. We want to make sure that it really works. We need to validate those hazard controls. We need to validate the analysis methods as well. And if we're going to use this for forecasting performance, it has to be reliable. So those are some reasons why this is important, why you need these tools in your toolkit. Let's first of all talk about some data formats. This will help. It's an introduction to these terminologies, but as you read it in other statistical self-studies you might take on, or reading an article in a professional safety journal, or as you're going through and listening to this lecture, understanding these data formats is important. First of all, keep in mind there's categorical data. This is the type of data you would see maybe on a survey when we're collecting demographic information. There's ordinal data. We frequently see this in a survey, a Likert scale, interval data, and ratio data. Let's talk about these individually. First of all, categorical data is simply that. We are separating responses. We're separating into demographics or some type of category. It only differentiates membership in a group. So there's no numerical value to being male or female or being in the second shift or third shift, other than the fact that the 2 and 3 denote a common accepted time frame when we think of those shifts. It doesn't mean that 3 is greater than 2. It just means I belong to this group versus that group. It's the least useful from a statistical analysis standpoint. Notice the term I used is least useful. It doesn't mean it's not useful. Obviously, when we do safety perception surveys, it is helpful to sometimes differentiate the responses from one group of employees versus another group of employees, because we can sometimes troubleshoot management commitment issues as they exist maybe on second shift versus first shift. So it is useful, but if we're talking about it from a numerical standpoint, a statistical analysis standpoint, it's the least useful. But it does have a purpose. That's why we track that kind of information on a survey instrument. So keep that in mind. Categorical data, we are just breaking things down into categories or groups. The numbers really mean nothing. It's just we select one to signify we're in second shift and two to signify that we're in second we select one to say we're in first shift, two to say we're in second shift, three to say we're on third shift. We could easily call it A shift, B shift, C shift, and we just put a number that demonstrates that. Then there's ordinal data. Pretty easy to remember this. It deals with order or ordering. This is the kind of data you frequently see when you're responding to the survey, not the demographic information I just mentioned, but this is where we're responding to the individual prompts on a survey. Usually it would be strongly disagree and strongly agree, 1 to 5, 1 meaning we strongly disagree, 5 meaning we strongly agree. We commonly call this a Likert scale. Keep in mind, there's no value comparisons in ordinal data. When you select 1 that you strongly disagree, does not mean the 1 has a less value than the 5. It just means this is how you are ordering your response to it. You strongly disagree with this prompt, this statement. Maybe the statement on the survey is, my supervisor consistently enforces safety rules. Well, if the employee responds to as a 1 that they strongly disagree, doesn't mean that 1 is less of a statistical value than the 5. It simply means this is where I'm at in the order on the scale. More useful statistically than categorically, but it's still low. Remember, we're just ordering things here. Obviously, safety perception surveys are tremendous tools. We value that data. But when we talk about statistical analysis, it's ordinal data. There's interval data, which is what we would talk about when we're talking about maybe a thermometer. It's a perfect example of interval data. It's a continuous scale. There's equality between the points on the scale. And 0 is simply a placeholder. Now, we have a fair degree of flexibility with this, and it's more statistically useful in categorical and ordinal data. Just keep in mind that 20 degrees Fahrenheit would represent a value difference between it and 10 degrees Fahrenheit. So there is some value and differentiation here between the points here, whereas on a Likert scale or the ordinal data, there's not. Then there's what we call ratio data. Much more useful. It's the higher degree of usefulness when we talk about a statistical analysis. It's continuous data. 0 is not simply a placeholder. It actually represents the absence of something. When we have a 0 number of injuries that we've had in a particular period of time, that means that is the absence of the injuries. Or maybe we also see the absence of unsafe behavior. It is the absence of something, where that's what 0 means. And there is magnitude between the values, and it is the highest degree of statistical usefulness for us, ratio data. Now that we've talked about the categories of data, let's talk about the different types of statistics that we would use. Descriptive statistics are those that deal with population. Examples of measures of central tendency being mean, median, and mode. Those are measures of central tendency. They're part of descriptive statistics. They describe the population. Then there's measures of variability, also describe the population, but they talk about variability, things like range, variance, standard deviation, and correlation coefficient. Those are the ones we're going to look at here in this class. And even within this, we can distinguish between inferential statistics and those statistics that we don't have to draw an inference from. But in inferential statistics means this is where we're taking a sample of something, we're drawing an inference based off the information, the data that we've got. It's usually when we're talking about we've taken a sample of something, we sampled a population, not the entire thing, we've just taken a sample of it. Maybe we sampled 20% of the workforce to try to draw an inference based off of that. That's kind of low. We want to, certainly in safety, have a bigger sample size than that, but sometimes that's the best you can do. We're always concerned about the distribution of the sample from which it comes from. So if we haven't looked at the entire employment and we've only looked at one narrow group, that could be a problem. So things we talk about, differences between means, chi-square, those are all examples of inferential statistics that we explore. We're not going to calculate chi-square here in week 5. We'll get to that a little bit later, but those are all examples of inferential statistics. Now, going back and looking at what we said, measures of central tendency, we want to look at these 3, mean, median, mode, individually. Calculating mean, most folks know it as average, is basically taking the summation of the individual items or observations or values and dividing it by n. N will stand for the total number of individual items, total number of observations, total number of values. You're going to see n used quite frequently. So you'll notice the sigma, that is the Greek symbol there, sigma x, means the summation of all of those values. Maybe there are 13 different values that we have, 13 different data points. We'd add those up, divide by the total number of data points to get the mean, or as you will see in the Microsoft Excel video, average. Now, median is the point where 50% of the values lie above and 50% of the values in this data set lie below. To calculate median, you arrange the values, items from lowest to highest, or you could even go highest to lowest. And you find the value in the middle. If it's an odd number, that's pretty easy. You find the middle value, and that is the median. However, if you have an even number, you're going to have 2 values or items that are in the middle. Which one is the median? Well, that's where you would take the average of the 2 in the middle, and that would give you the median. Mode is the most frequently occurring number, and there may be more than one mode in a particular set of data. So keep that in mind. Mode is the most frequently occurring number. If I had a set of numbers and 2 numbers appeared the same number of times, maybe I have a set of data and it's 1 through 5, and data point 1 is 22, and then data point 2 is 23, then data point 3 is also 22, and then data point 4 is 19, and data point 5 is also 19. I've listed 22 twice and 19 twice. In that situation, 22 and 19 are both the mode. If 5 data points, say data point 1 is 10, data point 2 is 9, data point 3 is 9, data point 4 is 8, data point 5 is 7. In that case, it's just one mode, which was 9, that appeared twice. Range is the difference between the lowest value and the highest value. It's a simple subtraction exercise there. You arrange the values from lowest to highest and subtract the lowest from the highest. Now, going back and reviewing, those are measures of central tendency. Mean, median, mode. Measures of variability are a little bit more complicated, but they many times tell us a whole lot more valuable information in drawing conclusions. So let's talk about those. Variance for a sample. Here you'll see the little theta square equals the summation of a particular value. In this case would be x, subtracted it from the mean, then that quantity square, plus the next value in our data set may be y minus the mean, that quantity square. And if we have other data points, this will keep going on in the numerator of this formula. And maybe the next one is z, a, and b, but it would be the summation. The numerator is the summation of each value subtracted from the mean and that quantity squared. The reason we square this is because we could see negative values up there. So anytime we're going to square that negative value, it makes it a positive. A negative times a negative is a positive. And then we divide it by n minus 1, particularly if we're looking at a sample of a population versus the entire population. And if it's the entire population, we would use n in the denominator. Standard deviation is simply the square root of the variance. Many times we're calculating standard deviation and what we need here in this class. So this is really the formula we're looking at. The standard deviation equals the square root of this entire quantity, meaning the summation of value 1 minus the mean square plus value 2 minus the mean square plus value 3 minus the mean square. All that makes up the numerator divided by the denominator, which will be n if we're looking at the entire population, and it would be n minus 1 if we're looking at a sample of the population. So if I surveyed every employee within the organization, and that means I've got the entire population, I would utilize this formula n. An example of this, maybe we're examining a particular item on a safety perception survey. Maybe it's that question, that prompt I mentioned earlier. My supervisor consistently enforces safety rules. And if we came up with we had a series of values there, we wanted to calculate the standard deviation. You know, the first person marked a 2. Well, that would be value 1, 2, and maybe the mean. If we looked at all of those and we calculated the mean responses to that, and maybe the mean is a 3.4. So the first person marked a 2. So it would be 2 minus 3.4, that quantity squared. Maybe the second person marked a 4. So that would be 4 minus 3.4, which is what we said the mean was, squared. And maybe the third person marked a 5. Well, that would be 5 minus 3.4 squared. So on and so forth until we get all the values in the numerator. And then we divided it by the number of employees who took the survey. That would be n. That's if we looked at the entire population. But let's say we only surveyed 50% of the workers. Same thing goes on in the numerator. It's just in the denominator, it's the number of employees minus 1. That's how we account for this sample of the population. So now we understand how we calculate standard deviation, what the formula means. Let's take a look at what standard deviation means in practical everyday terms in a way that you could explain it to someone else within your facility as you're talking about safety performance measurement, interpreting the results from a safety perception survey, and so on and so forth. And to do this, we're going to take a look at the normal distribution curve. Many of you will call this a traditional bell curve, and that would be correct. That's what we're looking at. We're looking at how data points lie in relationship to the mean in a particular distribution. Now, in this case, I'm going to try to pull up a drawing tool here if I can. And we're going to take a look. Here you will see this is the mean within this normal distribution. It is the area right in the middle of this bell curve. And if we were to look at all the data points that lie 1 standard deviation to the left or 1 standard deviation to the right, you would see that all of this data in this particular area account for 68.26% of all the data points. And then if we go out in another standard deviation to 2 standard deviations, both to the left and to the right, you're going to see we've now accounted for almost 95% of the entire data points here in this bell curve. And then obviously if we go on out yet again to 3 standard deviations, we're over 99% of the data points. So when we talk about standard deviations, we are talking about how the data points are spread in the distribution relative to the mean. So now that you kind of understand what that means or what it looks like graphically, let's look at a control chart, which is something you're going to be asked to do, and then we're going to try to relate this normal distribution curve to a control chart, which that takes me to this slide. Now, in this, you saw this back in week 4. It was utilized when we were talking about tools in the first 3 steps of the 10-step process for developing leading measures. We could have a control chart. Now, in this particular case, we're talking accidents or incidents. I guess the correct term or better term would be incidents here. If we plotted them out in a line graph, you would see the data points following along in a nice line, and we're connecting the dots, if you will. The data here, 18 in the month of January, corresponds to the 18, the first dot, and so on and so forth. You'll notice the line that goes through the middle here is the mean. That represents the mean, or x bar. The bar over the x is the mean. If we were to calculate the mean of all the incidents that occurred January through December, they come up around 19 point something, or very close to 20. And then we would have to calculate an upper control limit and a lower control limit. Now, there are different ways of calculating control limits, and it depends on the kind of data you have. Now, this can involve a fairly hefty lift in statistics and probably beyond the scope of this course. So we're going to keep calculating the upper control limit and the lower control limit. Very simple here in this class, and we're going to get there in just a minute. But as mentioned back in week 4, the purpose of the control limits is to set a boundary, if you will, for the data points. And it's when data is within these control limits that they can usually be explained by random variability, unless, of course, they go above a control limit or maybe below a control limit. Usually when we have data points that are outliers or exceed those control limits, something there has happened that's beyond the explanation of just random variability. Or we may have enough successive data points or enough successive data points at a particular control limit that are trending in a particular direction. And I'll back up just briefly. If we could have 3 or 4 data points that are very close to a control limit, and they are very close together, then that might mean something there is going on outside of random variability. Or if we have enough successive data points trending in the correct direction, then something there is going on beyond random variability. But all the other data points that are occurring within the boundaries of these control limits, we could easily explain them as being due to random variability. So, for instance, maybe we instituted a training program in June to address whatever this hazard is because something finally caused it to spike above the control limit. Well, we could presume that our training program is making a difference because we've had a few months of lower injuries. But it's not until we do some statistical analysis can we reach some kind of conclusion. Have we, in the wake of the training, post-training, seen successive data trends that would indicate the training is working, trending in the same direction? Now, that would take more than 1 or 2. We're usually going to look for 6 or more there. Or did we drop the incident rate below a lower control limit? Then that would indicate possibly, if the training timeline matches up with the reduced injury timeline, that our training is making a difference. Unless we do some kind of statistical analysis, whether it be through a correlation or whether it be through some type of control chart, it's hard for us to conclusively say our training's making a difference. If we don't have that tool, we're simply guessing. So what are the steps in making a control chart? I've tried to break those down into 3 succinct steps here. First of all, you have to plot the data on a graph, calculate and place the mean on the chart, and then calculate and place the control limits on a chart. Now, there are ways to get Microsoft Excel to do all of this for you. However, as simple as the examples are and the assignments are in this class, you could probably just calculate the control limits and just plot those or make a line on your control chart, and that would represent the control limit. And I would encourage you to take a look at the Microsoft Excel video that explains how to just make one of those lines appear on the chart. Very simple format. So now we've talked about a control chart, and I mentioned that I would like for you to understand this normal distribution as it applies to something that's real. Now here's what I'd like for you to see. As we look at this control chart, you can see that these data points are going up and down and up and down, and we're looking at this kind of linearly here. However, if you were to go back to that normal distribution, you would see that that normal distribution, if we were to turn that up on the y-axis, that's what you would see, the normal distribution. So these control limits actually represent some of these boundaries that we see here on a control chart. So this, like I said, representing the mean, and my drawing there is not totally correct, but if this is the mean, and we were to come over one standard deviation and one standard deviation, the data points that lie in this area would represent one standard deviation. Then we could go out here to these control limits, and based on how we're going to calculate them, similar to what you would see like in an X-bar type calculation fashion, would be two standard deviations. So if you were to look at that normal distribution, standard deviation, and you were to flip it up on the y-axis here, you would see that that normal distribution follows this accident control chart. So with that said, let's move on forward, talk about how do you calculate these control limits. This is a fairly busy slide. Don't be intimidated by the amount of information on it. It's really not that difficult. We're going to use a very simple method of calculating control limits. Some would even call this a confidence interval that we're placing here on this graph. And for the purpose of this class, I'm not going to correct you one way or the other. But here would be the formula if we were calculating numbers of events, such as the control chart I showed you earlier were numbers of incidents. They are not expressed in percentages or fractions, if you will. Here we're dealing with the numbers of events. The formula is rather simple. Here you will see the variables x equals the mean, z equals the normal distribution. Here, since we're using two standard deviations, which is usually what we're going to look at in safety and ergonomics, we design to the 95th percentile. And if you're taking a standardized exam, certification exam in safety, if you're in doubt, you can always assume we're going to utilize two standard deviations, which brings our normal distribution constant here, which is z, to 1.96. And then, of course, S here equals standard deviation. Now, notice I said of a population. It could also be standard deviation of a sample, which would change it slightly. However, we're just going to go with these three to demonstrate this. So to calculate the upper control limit, X would be to take the mean of the data points or the various ranges I have, plus the quantity, 1.96 times the standard deviation. To get the lower control limit, it's the same thing, except there is a subtraction instead of an addition. Once I calculate that, I come up with two numbers. The higher number represents the upper control limit, so I could just go and find that number on my y-axis and run the line straight across, and that would be my upper control limit. And I would go down and find the lower number plotted on the y-axis of my chart, my graph, and that would be the lower control limit. Now, if you were going to calculate this for percentages or proportions, using the same 95th percentile statistical significance, two standard deviations, we still use 1.96, but you'll notice the formula here is a little bit different. P here equals the mean proportion, whereas before X we were using was the mean number of events. Here would be the mean proportion. So P is that as whatever maybe our rating is the mean percentage of percent safe behavior was 54%. So 0.54 plus the quantity 1.96 multiplied by the square root of that mean proportion multiplied 1 minus P divided by N. Again, if we're using N, we are calculating based on the a sample, the entire population, I should say, and not a sample. N minus 1 would equal the a sample instead of the entire population. So those are the formulas for calculating the control limits. So going back to saying, how do you make a control chart? Well, first of all, you got to have the data. You plot that out on the graph, a line graph. Then you would have to obviously calculate the mean and place that mean on the chart. And then you would calculate the control limits, which is where you use these two formulas, depending on whether you're dealing with a proportion or percentage or whether you're dealing with the numbers of events. Calculate that and then plot those. And then you could graphically see how the data is distributed there. Keep in mind, and I'm going back one more time, trying to circle back, back to this normal distribution, is that the tighter the standard deviation, that means, or the smaller the standard deviation, that means the more tightly packed the numbers are around the mean. I'm going to give you an illustration, a real world illustration from my personal experience. Uh, Working with an organization once and was doing some consulting for them and did a safety perception survey. And we were surveying this organization and how effective one of their hazard controls were. Management thought this was a great control, and we wanted to see, do the employees share this same sentiment that this system that they had in place really worked. So we had surveyed the employees using a Likert scale, and we asked 3 or 4 different prompts, all dealing with the same construct about the effectiveness of this. The employees who were surveyed, which was about 60% of the population, came back with a mean response on a Likert scale, 1 to 5, at 3.2, which, if you think that's one of your best hazard controls, you would hope the mean response, the average response, would be higher than 3.2. So that was number one issue to take a look at. But then when we looked at the standard deviation, for a Likert scale, it was quite large. It was around 1.4, which means it would the 68% of all of the responses from the employees were somewhere between 3.2 plus 1.4, that would be 4.6. And if we take 3.2, the mean, and subtract the 1.4, that is going to give you around 1.8. So the data was very widespread around the mean. There were some employees that thought, yeah, this hazard control is great. And there was another group of employees that thought, oh, it's horrible. And it pointed us that, hey, there is a need for us to dive deeper and find out why are the opinions so spread out. So then we were able to look at some of the categorical information and find out it happened more on certain shifts than it did others, and really kind of narrow down some management causes. So looking at how big or how small the standard deviation is tells you how closely does the mean actually represent the whole entire data, whole body of data. So I hope that helps you understand the practical application of standard deviation. Obviously, the wider it is, the more widespread our data is, the tighter it is around the mean, then the less widespread the data would be relative to the mean. So let's go back forward now. We've talked about control charts. We've talked about calculating standard deviation. Let's talk about correlations. This is something else that another tool that we need to have in our toolbox to determine, are our hazard controls working? Is this activity, this safety activity, worth measuring? Is it something we should invest our time in? Does it need to be fixed? So we can compare 2 sets of data. This is what we would call a 2-variable statistic. We have to have an X value and a Y value. Those 2 values are tied together. And we would see over time, over a plotting of the data, whether we have a strong positive correlation, meaning the more we have of X, we have a direct proportion increase in the Y value. And if you recall, maybe from algebra, we're talking about a slope of 1 here. That means for every 1 digit, the X value goes up, the Y value goes up a corresponding 1. That's kind of what we're looking at here. A strong positive correlation is going to equal or be very close to the number 1 if we calculate the correlation coefficient. A strong negative correlation, as you'll see, as X goes up, Y goes down proportionally with X. And the more that slope is closer to a 1-to-1 type ratio, the more strong we'll see the correlation, whether it be positive or negative. Now, when the data points are kind of scattered out like they are here in the middle, and if we were to calculate the correlation coefficient, it would be close to 0. We call those weak correlations. Now, you'll notice here on this particular, and I'm going to draw here again, this particular week, you'll notice the direction is going positive. However, the data points are kind of scattered out, kind of widespread, which is telling us it's a weak positive correlation. Positive because it is heading this direction, weak because the data points are not a nice tight pattern like we would see over here, where we have something more akin to a slope of 1. And over here it's just negative, meaning the more we have of x, the less we have of y. Now, if we've got a control in place that we want to see the more we do of the safety activity, the fewer incidents, we want a strong negative correlation. But if we want to say, hey, are our observations working? The more observations we do, we would hope we would see a proportional increase in safe behavior. That helps us tell whether our hazard controls are working or not. So correlations are very, very beneficial to us. Now, we could plot this out, and maybe we're looking at quarter data. Here, obviously, the quarters are more of a placeholder here than they are an actual value. But we would hope that we see a proportional increase of safe behavior, or I should say, proportional decrease of incidents, as we see an increase of safe behavior. And the lines here in this graph represent the two data points, whereas the quarters are, like I said, simply placeholders showing how it's progressed over time. This is more what we would want to see. This would be at least a negative correlation, but you would see it is not strong. And here we see a positive correlation, but again, not strong. We would hope that the more observations we have, we would have an increase of safe behavior. And actually, if we look here toward the latter quarters here, it looks like safe behavior is tailing off, when indeed number of observations are going up. But we saw a flip side on the beginning, and that's why if we looked at data plotted as a whole, it shows that it is a weak positive overall. Now, I will go ahead and tell you that this would be a strategy for taking the CSP exam. You could actually have the two binomial data sets, like an X and a Y, that correspond to one another. And then you could just draw yourself a little graph, plot out points where you've got a scale of an x-axis and a scale of a y-axis plotted out, and you could get pretty close to knowing whether your answer should be a strong positive or whether your answer should be a strong negative. Meaning an answer close to -1 if it's a strong negative correlation, or +1 if it's strong positive. And get pretty close. And you many times on those exams narrow it down to 2 answers. But if you're wanting to get a precise calculation of the correlation coefficient, you would utilize what's called the Pearson correlation coefficient. Now, here's the formula. On its surface, looks pretty intimidating, fairly long formula. And in this class, we're not going to spend time doing that, because I always tell students, use a calculator with a stats function to calculate this for you, or as you got the luxury in this class, you can utilize Microsoft Excel to calculate R. R always equals the Pearson correlation coefficient, almost always shortened to correlation coefficient. Solving for R. Once we solve for R, we're going to have a value somewhere between -1 and +1. When the value is close to a +1 or is +1, we know we have a strong positive correlation, meaning the more we do of X, we have a proportional increase in Y. Strong negative, the closer the value is to -1, meaning the more we have of X, the less we have of Y in a proportion. And then when it's closer to the 0, maybe it's -0.2 or +0.2, we know there's no correlation or a very weak correlation. Maybe it's a -5 or -0.5 or +0.5. We know we have either a weak positive or a weak negative. So this is the scale when we calculate correlation that we're working on, -1 to +1. And like I said, utilize Microsoft Excel, utilize a calculator to come up with those calculations. I want to share something else with you, even though not really covered on the assignments. In week 5, it is something that is worth mentioning. Is another formula always on the CSP exam study materials that safety students should be made aware of. And this is, how can we solve, or how can we know we're taking enough samples, or we're doing enough observations that we can rely on the information that we're getting? And this is always beneficial in looking at what is the level of accuracy of the number we're getting when we're doing observations of behavior. Now, this is a formula. It's presented in a lot of the CSP study materials. It's n equals 4 times the quantity 1 minus p divided by the quantity s squared p. And the variables are explained here on the right. N equals the total number of observations or samples that we would need to reach a certain desired level of accuracy. P in this instance is the percentage or proportion, whether it be safe or unsafe. And S, we pick S. What would we like to have as our level of accuracy? Is it plus or minus 10%? Is it plus or minus 5%? And when we solve for n, we know exactly how many observations we have to make to get to that desired level of accuracy. Now, obviously, we could use some basic algebra, rearrange this formula, and we could find out what is the level of accuracy we have utilizing the number of observations we made. And we would simply, multiply both sides by n. Divide both sides by n. And then we would also multiply both sides by s squared and solve it that way. And we could rearrange the formula and solve for s squared. But we're going to solve for n just to prove a point here. I'm going to give you an example. Let's say we are wanting to find out what's the reliability of our observations. And the observation is safe forklift operation traveling in a warehouse. And if you've done much with behavioral safety, you know that being precise on the behaviors is critical. And when we take behavioral inventories or when we're doing observations, because the reason folks may take risks driving forklifts in one area of the facility could be different than another area of the facility. So here we have a nice, precise, specific behavior that we want to observe, and it's safe forklift operation traveling in a warehouse. Let's say we went out, we took some observations, and of the observations we had 75% safe. That basically means 3 out of 4 people were operating the forklift safely while traveling in the warehouse. Let's say we would like to know that it's plus or minus 10%. That's the accuracy level that we're trying to get to. Well, if we plug that into the formula that was presented before, n equals 4 times 1 minus p, or that quantity 1 minus p, divided by s squared p, we plug that in, the third bullet down, you will see that's what it would look like. 4 times 1 minus 0.75 divided by 0.01. Now, remember, we are having to square S. S is squared. So some of you are like, wait a second, 10% is 0.1, not 0.01. Remember, it is squared, so it's 0.01 times 0.75. If we plug that in, you would see we'd need 133 observations to have a 10% accuracy level in our 75% safe assumption. Now, that's a lot of observations if you only have 4 or 5 forklift operators. The point of this being, and I want to finish this segment on this point, is that we are going to do our very best to get as accurate of measures as we possibly can. But sometimes it is very difficult to get to the bean counter level of accuracy, plus or minus 3 or plus or minus 1%, simply because we just don't have the kind of data pool within a particular organization, or maybe a particular shift, maybe it's third shift, to come up with that. However, we do know operating forklifts safely is very important because it presents fatality and very serious injury risk. So we're still going to, take a look at those numbers. It might be part of the mix of safety measures that we're focusing on, even though we can't get to the accuracy level that some, maybe in the accounting or engineering world, would like to see. We're still going to look at it because we know it's important. We're going to strive to get it as accurate as possible, but we got to keep in mind there's some limitations based on the data pool that we have. So that's really the end of the math and stats fundamentals lecture for week 5. If you have any questions, please don't hesitate to forward those to me or to your facilitator. Thank you.